In this video, we're going to derive or maybe prove the law of sines. And to do so, I'm going to first start off with just some general triangle. So I've constructed triangle ABC. That represents any triangle, whether it be isosceles, right, or just oblique, just some random triangle. And if I want to talk about sine, a trig function, I really need a right angle. So right now I'm not given that. So I think what I'll do is I'll construct the altitude of this triangle. So I'm going to draw H, maybe for height, but draw H, the altitude. So from angle C, I'm just going to drop a perpendicular line to that base AB. So I just draw a line straight down in such a way that it meets perpendicularly with line segment AB. And I'm going to call that little h. I should also finish labeling the triangle. If my angles are capital letters, then we label the corresponding or their opposite side lengths with the same letter but lowercase. So CB I could call little a, AC is little b, and then this whole AB is lowercase c. Okay, generic triangle ABC, I've drawn the altitude, and by doing so, I've now created two right triangles inside my original triangle ABC. Okay, now I can start to talk about sine. So there's some things I'd like to notice. First, I want to notice what happens when I try to evaluate sine of angle A. Well, if I use the SOHCAHTOA definition of sine, sine of an angle is defined as the opposite side length over its hypotenuse. So sine of A will be equal to the altitude h over the hypotenuse little b. Similarly, if I go off and try to look at sine of angle B, it will be its opposite side length over its hypotenuse, h over A. Now, both of these equations use that altitude. So I think what I would like to do is solve both equations for h. So I'll simply multiply both sides by b. And over here, I'll multiply both sides by little a. Now I have that the altitude, or h, is equal to b sine a, and that same value is also equal to a sine b. So if h is equal to this, and h is equal to that, then by a transitive property, I can say this is equal to that. So I'm going to do that next. I'm going to set these two equal to each other. B sine of A is equal to A sine of B. Now this relationship is called the law of sines, but typically you'll see it written with the same letter on the same side of the equation. So I'm just going to pretty this up. I'll divide both sides by little a and divide both sides by little b. So we have sine of a over a equals sine of b over b. I'm not quite done yet, but before I continue, this is extremely powerful. I started off with just kind of like a random triangle ABC with no right angles. And before today, I didn't know how to relate these angles with those side lengths. Up until now in trigonometry, I needed a right angle in order to relate opposites and adjacents and certain angles. Now though, this relationship right here, sine A over A equals sine B over B, this has four unknowns. So if I know three of them, let's say I know those three, then I can solve for that unknown variable. So if I know one of these angles, its corresponding side length, another side length, I can use the law of sines to find that unknown value. And I don't have to use trig. This is just, I don't have to have a right angle. I can use this relationship. All right, let's go back to this construction proof. So if I had drawn this altitude from a different vertex, let's say from vertex A, if I had drawn the altitude like this, then I think you could similarly see that the law of sines would spit out like sine of B over B equals sine of C over C. So if I just redo this process, this is also equal to sine of the other angle over its corresponding side length. Now, I didn't show any work for that, so I'll just say something like similarly. And that just means, if you see this written in the proof or somewhere, that just means I didn't maybe show the work for this, but if I were to just repeat this process, I could come up with this relationship. We call this the law of sines. It's very useful when we're trying to find side lengths or angles of a generic triangle. All right.